for a lot for an object that is experiencing an unbalanced force, its motion is going to change. And so we're talking about translational motion. It's going to change how fast it's going or what direction it's going. For rotational motion, it's going to spin faster or spin slower. Now, this part is the hard part. All of this is tempered by inertia. Now, if you don't remember the definition of inertia, I want to remind you. Inertia is a measurement. It's measuring a property of the object. For translational motion, inertia represents how effective a force will be at changing an object's motion. I'm using different vocabulary than I used first semester on purpose. But measuring an object's inertia is measuring how effective a force will be at changing an object's motion. Similarly, rotational inertia is measuring how effective a torque will be at changing how an object spins. Again, for rotational motion, it's changing how effective a torque will be at changing an object's spin. Now, this idea of effectiveness, I hope you understand this. We're talking about how much the object's motion is changed by that unbalanced force. So this is trying to find a way to put words to Newton's laws. A simple way of saying it, the simplest way, if we're talking about forces, big things are harder to move than small things. You already know that. The thing that I need you to understand is that even though you can say those things out loud, the moment you guys write this down, you tend to lose all sense of what this is about. But this statement is exactly what I just said. Objects that are big are more difficult to change. If this number gets bigger, this number gets smaller. Right? So if you push on a big table, M is big, A is small. You push on a small Hot Wheel car, M is small, so A is big. It's how effective that force is. This part is how hard you push. Right, that's what that part is. This part is what happens. Specifically to V, right? What happens to its velocity? It's going to change. Just how much? What happens to it? This part, this is the inertia. This is the part that's resisting changes. That's why if you have bigger things, they are harder to change than smaller things. Look, half of you experience this in the hall every day. You're walking down that 100 or 200 hall with all those other people. I'm afraid to say some of you are kind of small. And some of those people are kind of big. And when you guys are in a conflict, the smaller people get pushed around more than the bigger people do. It's just a fact of physics. There's nothing you can do about it. Now, this is also true when we talk about torque. Some things are harder to twist than others. It's all the same. I mean, these statements, it's different letters. I get that it's different letters, but this part right here, this is how much you twist or turn. And maybe how much isn't the right word there. Maybe how hard you twist or turn. We can use the same words here. So let's say how hard. Right? It's how much you twist or turn something. The drill does a good job twisting and turning for you. You guys who have used it. If you had to do it by hand, it'd be harder. This is what happens. again, this is something observable. What happens to omega? Its spin. Does it get faster? Does it get slower? And last, but certainly not least, this I is still inertia. This is the thing that's resisting those changes. Something with more inertia is harder to twist or turn. So all these things are the same. I'm just reiterating it from first semester. But here's where we get some divergence. So I'll move this back up here. I kind of want to leave these visible. But when we talked about inertia here was just mass. That's it. We treated our object as a point. We drew all the arrows on it. But how effective those first forces were was basically how much mass the object had. More massive things are harder to change. That's not true for rotational motion. For rotational motion, inertia is a bunch of things. Mass is among them. So mass plays a role. But what's more important is how far the mass is from the pivot. That makes a bigger difference than just the mass. In fact, the third part of this is the shape of the object, which is also a lot about how far the mass is from the pivot. So although when it came to just moving an object from one place to another, all we cared about was the mass, but when it comes to spinning an object, the shape of the object matters. And the most important quality is how far from the mass is the pivot point. Now, like everything else in physics, the moment we start talking equations and math, you guys have your eyes gloss over a little bit. But the math is just trying to find a way to say this mathematically. That's all it is. So when we said it, bigger things are harder to move. Newton was trying to find a way to say it mathematically. That's all that is. And this is Newton's attempt at saying it mathematically. Similarly, for twisting and turning, Newton's attempt at saying it mathematically. The problem is, how do we put this into math? How do we describe this ability to twist or turn something? How difficult it might be based on an object's shape? There's a way to write it, but the moment I do, I put an equation down and you guys get a little weird about it. But again, I want something that says, here is the inertia of the object. This is how you figure out why some objects are harder to turn than other objects. So here's what we have to do. Moment of inertia is the measurement we use for rotational inertia. So saying moment of inertia is saying rotational inertia. I need an expression that talks about the mass of the object, sure, but also how far away the mass is from the pivot point. Now, look, our objects are things like this. If this object is going to pivot, well, this whole object is pivoting about this point. But some of the mass of this object is over here, and some of the mass of the object is over here. But our definition of inertia says that mass that's further away counts more than mass that's closer to the pivot. So I need an expression that does that. And what it looks like is this. It says, okay, here we go. Take your object and break it up into pieces. So take our meter stick, we're going to break it up into pieces. The moment of inertia is the sum of the inertia of each piece. Okay, the moment of inertia is the sum of the inertia of each piece. The further away the piece is from the pivot, the more it counts. The further away the mass is from the pivot, the more it counts. Here's how we write it mathematically. Are you ready? This is the mass of a piece. I put M with a little I there. Say it's piece number I. R is the distance from the pivot point to that piece. But it just so happens that R is more important than M, and so this is squared. We do that from piece number 1 to the last piece, N. This is how you write a summation. And I know some of you know what summation symbols look like and some of you don't. So we're going to use a simple object as kind of our basis of discussion. We're going to look at a meter stick. And we're going to talk about taking that meter stick and rotating it about its end. So this is where the pivot point is going to be. Okay? Now this is just one big object. But hear me out. This says to take the object and break it up into little pieces. And then find out how far each piece is from the pivot point. And square that. And then go on to the next piece. And then go on to the next piece. And then go on to the next piece until you've added up the entire mass of the object. Now, I'm looking at the meter stick real quick, and I want to impress this upon you. And we're going to use a meter stick as our example, and we're going to try and break this up into 10 pieces. So I'm just going to draw a couple of lines in here to break this up into 10 pieces. You guys have like rulers and stuff, so maybe, but it doesn't have to be super neat, just pretty close. Somehow I broke mine up into 9 pieces because I wasn't paying close enough attention. You should expect better of your teachers. There, 10 pieces. I've broken mine up into 10 pieces. Did you break yours up into 10 pieces? Okay. Now, I said meter stick, and I mean meter stick because I want to use the meter stick as my example, but when I'm done, I would really like to be able to apply this to anything that's long and skinny. Because remember, the idea here is we're trying to figure out the inertia of different shapes. So my arm is something that's long and skinny. If I rotate it, it has a moment of inertia about its end. So if I can figure out something I can apply to anything long and skinny, then I can probably apply it to any object like a stick or a baseball bat or a golf club. All of those things would be similar. They'd have a very similar moment of inertia because they're long and skinny. Does that make sense? So instead of saying that this is 60 grams and 1 meter, I'm going to say it has a mass of M and a length of L. So that at the end of this, I could just put any meter stick in here or any stick at all. Does that make sense? It may not make perfect sense right now. I think it'll make sense at the end. So here's what we're going to do. I think that this is an obvious thing, but can we assume that the center of mass of each piece is at the center of the piece? Does that make reasonable sense? So there will be 10 of those, 10 centers. Okay. Again, let's look at our summation. Our summation tells us this is the moment of inertia of a rod about its end. We're going to say sum from piece number 1 to piece number 10, because we're doing this for 10 pieces. Take each piece's mass, multiply by the distance away from the axis of rotation, and square it. So let's write our summation. Let's start with piece number 1. If I take a meter stick of mass m and break up into 10 pieces, what's the mass of one piece? M. Perfect. 1/10 times m. That's the mass of each piece. So our first piece has a mass of 1/10 m. That makes sense? Okay. Now we have to multiply by the distance from here to here, right? The distance from the axis of rotation to the first center. Now, we're breaking up into 10 pieces, but this is at the middle of the first piece. So if the whole thing is length L, how far is that? I'll help you out. This would be 1/10 of L. So what do you think this is? 1/20th of L. Perfect. All right, we have written it out for the first piece. Ready to go to the second piece? This does get easier because the second piece has to have the same mass as the first piece. I'm breaking it up into 10 equal pieces. So 1/10 m. Unfortunately, we are not 1/20th, but we're here now. Can you figure out how far away I am from the axis of rotation? 3/20ths. That's right. Do you see it now? 1/20th, 2/20ths, 3/20ths. Do you see a pattern developing? How many of you see a pattern developing? Okay, so if you're seeing a pattern developing, don't wait for me. Go ahead and run off. But I'm going to say all the things for the next piece, hoping it clicks in for everybody else. I'm on piece number 3. That's right here. How many 20ths is that one away? That's right, 5/20ths. So do you see it's just going to be all the odds until we get to 19? Now, I'm not writing them all out, and you'll understand why in a minute. So you might want to kind of follow along with this too. And you do understand why we're not doing this for 100 now, right? Okay. Do you notice that there are some things that are the same about every one of these terms? So can I just go ahead and take out the 1/10 m because it's in every single term? Do you also see I could take out 1/20th L because it's in every term? If I take out 1/20th from L here, I'll just get 1 squared. If I take out 1/20th here, I'll just have the 3 left, so that'll be 3 squared. If I take out the 1/20th here, I'll have the 5 left. That'll be 5 squared. Do you guys see that okay? Some of you don't, and I'll just consider this for just a minute. 5/20th L squared is also it's also 1/20th L times 5 squared, right? So if I take out the 1/20th L from every term, I'm left with just these numbers. It is true. I'm hoping you'll see that. Yep, I have to keep the squareds because they're all squareds. So if I take those out, I'll be left with this one, 1 squared, plus this one, 3 squared, plus this one, 5 squared. And now I am going to write them all out. What's next? 7. Next. 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 Excellent. Next. All right, next. Running out of space, Mr. Shelton. I have all the space I need. Plus, there we go. Wow, it's a lot. Now, we need to add all those up. So, you have calculators. I'm going to do the outside part. You guys do the stuff in the parentheses. Just add all that up. 1 squared plus 3 squared plus 5 squared plus 7 squared plus 9 squared plus 11 squared. I assume you have your squares memorized, but maybe you don't. The outside is going to be 20 squared, that's 400, times 10 is 4,000. This will be ml squared over 4,000. Now, we have 1 minute, so we need this number quick. It is 1330. Let's make sure somebody else backs me up, but I'm pretty sure I remember from doing this the other day. It's 1330. 1330, you got it too? Yeah. 1330. So, pay real close attention real quick. This would be 1330 divided by 4,000 ml squared. 20 squared times 10. So that, I believe, is 0.3325 ml squared when you divide out 1330 by 4,000. Now, again, guys, this is an estimate for any long, skinny object about its end. Now, tomorrow, I'm not going to be able to show you this, like I can't prove it to you, but if you actually were to break this up into, say, millimeters or smaller, you would get 1/3 ml squared. So we did pretty good breaking up into 10 because 10 gave us 0.333, right? So we did pretty good, but we can get better. All right.